Yeah. I will hand over the screen and the baton to you so you can start telling us a little bit about what Krebs is and why 3D printed molds have helped you.
All right. Thank you for the introduction, Dyson. My name is Tobias. I am the head of the R&D division here at Krebs Company, and we've been playing around with the 3D printed molds for almost 8 years now. And that is why we're here today, because we keep on facing new challenges, and now let's start this new company. So why not join forces and see what can lead of this as well. Let me just share a short presentation. All right. Let's see here. About the agenda, what I want to present for you guys today is just briefly giving you guys an introduction to Krebs Company, which what type of company is this, what our background is, and then today I brought along 4 different cases about what we have done in the printed tool, and they all have a different perspective on it. So hopefully you can see a project where it could match some of the projects that you maybe stand with at this point in time. Then I'll just summarize up the short presentation, and then we have a Q&A in the end if you guys have any questions you want to follow up. And as I said, my name is Tobias. I have a background in mechanical engineering, and I've been with this company now for 7 years. And the service here at Krebs Company is we are a sub-supplier of injection molding and injection blow molding as the core factory part of the business here. But then we also offer support in design and prototyping along with this hybrid manufacturing where we combine the printed tools and steel inserts and whatever we need to provide the fast and prototypes so that our clients would like us to make. But if we start at the high volume production, so the company has been established since 1956. So we've been here for quite a while. At the moment, we have 45 employees and 36 injection molding machines ranging from 15 to 400 tons. Then we also have 3 injection blow moldings machines that are running 24 hours a day. But we also have some clean room facility with some certifications, as you can see here. But the change in the core business philosophy, we're a family-owned company, and about 10 years ago, the son took over the company and hence started the R&D division to be able to renew itself and to be able to compete with just lowering prices from Asia and whatever. And I'm heading the R&D division, and in the R&D division, we do quite a lot of different things. We both do a lot of R&D support for other companies while they are going into fully automatic tooling, but we also do a lot of prototype and low volume production. So we both assist clients with mold design. We also do direct 3D printing for the first initial prototypes. We do freeform injection molding, which is this dissolvable resin that you can inject in and then dissolve whatever we have printed afterwards. But we have also done a lot of cases in just 3D printed split molds, that meaning we can just assemble a mold of looks like a Lego set, then we inject it, and then we manually take it all apart again for the first initial prototypes. But this is a fast way for us to making a lot of prototypes at a cheap cost in the early stage of the development. But what we experienced throughout time is while we assisted companies and clients from the very first prototype to the first injected parts, is that they are also on a ramp up production. So we also have added, now we're doing aluminum soft tools just for the range between 500 to 1,000 parts all the way up to 10,000 shots before we want to go into fully automatic tooling. So there was a bit about the background of our business. So we've been going around for 8 years now of R&D work, and we grew in 2017. We started out with 1 R&D engineer and 1 printer, actually the first AdiFab printer on the market. And today we have 5 full-time employed R&D engineers. We have 14 wet polymerization printers. We have 5 high-end FDM printers and 1 freeformer that is Arburg's pellet printer. So you print with all our natural resins that we normally use for the injections machines. So over the course of the last 8 years, we've done more than 100 projects in printed molds. We've done a lot in 2K, both with plastic on plastic, but also overmolding of metal inserts. We have worked with a lot of advanced engineering materials and now also fully automatic tools for small batch productions. So this is just a bit about who we are, where we are, and how do we got here. And now I have today the 4 cases that I would like to tell you a bit about. So the first one you have here is our Toyota case. The Toyota had an internal R&D competition throughout their multiple sites over the world, and the R&D division from the Netherlands won the project. They have developed and designed a CO2 capturing device that you can see here, and it's supposed to be consisting of 20 identical pieces as this, and then they are connected. But the problem, or not the problems, but the challenges that we had with this part was that, first of all, it was the overmolding of a metal grid along with 2 connectors in both ends. Then we needed to ensure that the water tightness of the part and the waterproofing was enclosed, because this was a product that would need to let air flow through to capture the CO2. But that creation also had some challenging creation of an internal channels here where all the airflow should go through. And because of this challenging internal channels, we choose to make this mold as a dissolvable photopolymer. This is the one that we have, that's X mold, so it came from the Nexa branch, where we are able to have resin on the inside of these bars here, on the ribs here. And if you had to do that in an injection molding tool, then that would be very difficult, or maybe not even possible, or maybe you wanted to solve it in a totally different way. But we ended up solving it with being able to dissolve all of this inside after we injected it within a few days. Then one of the other challenges, we have to overmold the metal grid here. You can maybe see it. The metal grid is here on the side of the mold, and here we have enlightened it before we dissolve the mold. And the way to make this was pretty difficult, because we needed to, when you're overmolding any metal part, you need to be sure that it would not move throughout the process while we inject with a high pressure, high temperature materials. We need to be fully sure that everything will stay in position. You need to make sure that all the plastic will not flew into any of the metal parts. So you need that sharp edges all the way around. So this mold actually ended up consisting of 22 individually printed parts that we assembled into one before we injected it, and then we dissolved one again. So a pretty complex and difficult part to make, but even more difficult if you wanted to make it in a conventional tooling. One of the other challenges was that we needed to make everything airtight. And as I said before, one of the challenges is also to make sure that we have all the metal parts staying in place while we inject it with the high-speed plastics. And the flexibility of the resin here gave us an advantage, as we could, as you can see here, print 2 inserts that would clamp around the 2 connecting plugs. And then while we insert this into the mold and then tighten the entire mold together, this one will fixate the metal piece so it won't tilt or tilt while we are injecting, and the material flow will come from one side to the other. Then we also needed to make sure that there's no plastic going on the inside of these air ventilations. So we designed some tight-fitting plugs that we again could make sure that it would fit really tight into the plugs. And again, while we are dissolving the rest of the mold, this one will also dissolve, and we have a working airflow ventilation again here that's airtight. this was a bit about the Toyota case. Then we have one of our other stories. It's a product we are part owner of now. It's a cavity that does eye tracking system for home monitoring of dizziness. There's a lot of when you're suffering from dizziness attacks, it can happen throughout the entire day. And so far it's been super difficult for doctors to find out what's the cause of it. So this is a device that you can get from the doctor. You can bring it with you home. And then when you feel the dizziness attacks arriving, then you can put on the goggles and then it would record the movement of the eye to help the doctor find the reason for the dizziness. Yes, so this is a bit about the background. And our core challenges with this part was that it needed to be a medical device. It was super important that we had no light penetrating the mask at any point. And then it needed to be food or skin contact approved. So we started off with designing this part. We have the three first casing here. You can see the electronic casing, the mounting plate where we mount all the electronics. Then we have the goggle, and then we have the lip. The first three parts here, we directly 3D printed them because the project, when we got in on it, were ready for clinical trial and got a lot of got all the approval. So we needed to move fast, but we were not able to directly 3D print a lip that would have a fitting that would fit tight and would be both medically graded and make sure that it didn't have any light going through. So to solve this one, we designed the lip just in a split mold. And this was the reason, because here we could get the medical graded material in a soft TPE that was flexible enough to fit on as many faces as possible. Because as this was one device, we needed to be sure to fit both on a small head and a big head. So this was the reason why we ended up going into a split mold, but we could make a turnaround in this within 2 to 3 weeks before we had the first trial out at the customers. The next part here is our QuickFact product. It's a product to take a stool sample, and it works the way that you insert it with a screw in the holster in the bottom. Then you can turn the screw 5 to 10 times to make sure that the sample you collect will move up the screw and be locked in the chamber above the screw. Then when your sample is done, you can retract the screw just half of the holster's length, and then you would have the sample locked inside the holster until you needed to take it out again so you don't make a mess. And the challenges for this one was that we needed to overmold, 2K overmold a sealing on the screw. And the difficult part is that the holster, for it to be made, it needed to have an inside draft, so we were able to remove the core of the holster. So that meant that the sealing slips needed to be tight fitting at the bottom position, but also at the top position, even though there was a difference in the diameter inside. That also meant that when we needed to turn the screw, it could not have too much resistance, because then it would get too difficult to turn it. So the way we ended up solving this was we ended up doing 10 different sizes of sealings just as a print on one print plate. So the next day we were out in the injection machine. I could try out different sizes, different length. And you can also see that this one maybe has 2 sealing lips on it. And then we were up to both doing this as a screw. We tried with 3. We tried with different formats that we can test out what worked the best. And this is also one of the things that we normally experience, that the way that we print the molds can actually move the process along a lot faster, because at this point it only took us a day to finalize how we wanted to make the sealings, and then we were able to replicate on the other 50 parts that we needed to produce for the clinical trial. And one of the things that we are really proud of with this product is we got in it at the very early stage. So we were also happy that we can give some information and help the product to be manufactured or designed for manufactured. So at the moment, we had it 2 years ago in the very initial first 3D printed how it would look like assembled, and now we have it full running in automatic production out in our facility. So the way that we can transit all the parts that we have, that all the design for manufacturing updates we can do along the way while we fastly iterate, is stuff that we can take with us while we then go into full production, because we had already had many of the learnings with us already. So when we then are able to go into production, then a lot of the problems we have already solved. And the last project I wanted to share with you, it's we call it the gear, but it's a gear that's inside a device, and the device is hourly taking blood samples from animals. But the company here had done the first prototypes in a direct 3D printed part. So they have it consists of, was it 10 to 13 parts, the first device they made, where all the parts were directly 3D printed, but now they needed to scale. They had an order of 100 devices that they need to deliver on, but then they also needed to enhance the quality of the part to ensure the life expectancy for the part while it's being mounted on the animals. So the way we solved this was assembled by 15 different parts, and 100 different devices needed to be assembled and made. So we, instead of just going the regular where we 3D printed the first mold and manually had to open it and take every part out, this one was installed into our automatic tooling, automatic mold. So we have a mold base, as you can see on this side here, where we are able to install different sizes of inserts. And then we can keep an automated production like this. And then we could shift even between the different sizes in this mold base that we have at the moment. So this is one of the other projects where we are able to help companies in the upscale, where we see the most people having trouble to finance just the first 20, 30, 50, 100 parts that they need to assemble to get the next step in their development. So to sum it up, like the 4 different cases that we want to show with you today. So we have done a lot of projects with a high complexity. That's why we really fun to use the dissolvable resin to fix many of the parts and the trouble there is with them. Then we also do a lot of medical devices, especially for a clinical trial, the first few production lines that people need to get out and get tested to get the next funding round going. And then we have the small batch volume production, which are installed into automated tooling or automatic mold. And that's the next phase where we see people need the support from going from the first prototype to just upscaling to the next level. So yeah, all in all, we've done more than 100 projects in 3D printed molds. This is just a few of them, and a few of those we actually have something left to show you guys, because many of the ones that we actually make, we either dissolve, and whatever part we make gets the customer. But yeah, so this is just a bit about what we do here, and hope you guys found it interesting enough and helpful.
Well, thanks a lot, Tobias. I certainly found it to be interesting. And one of the things that always fascinates me about you guys is the scope of application of what you do with 3D print molds. That has always been a source of inspiration. And well, I'm glad to see you're still evolving on the technology. I haven't received any questions from the audience yet, but I anticipate that some will come. In the meantime, I could perhaps start by asking you if you should compare what you guys do with the 3D printed molds with other types of prototyping services that are out there. What would you see as the key difference? What does it help you do that customers need?
I think the biggest thing for us that we experience the feedback from our customers is iteration speed and the short lead time. at least that's what we brand ourselves in being capable of. Normally, we could receive a part within the same day. Then we can design the mold, print overnight, be able to produce the first prototypes the following day. So I think everything that is about fast and needing tempo and needing, especially then also the parts in the correct material, is the projects that we really feel like are home runs both for us and for the customer, because that is where we really see the need of being able to produce fast prototyping and iterational speed. Yeah.
I had the pleasure of being part of the Toyota case study as well, and you were talking about this challenge of having metal inserts in a mold. I operate from the assumption that you would normally have to have a very, very high precision metal mold if you wanted to clamp around metal parts. Simon Pernetas is asking, could you give feedback about resin? I watched why you used the blue one. What are the difference from the others? So that's one for you.
Yeah, we have a few resin. As I stated in the beginning, we also have a lot of different printers, which is also giving us availability to a lot of different types of resin. We have a few dissolvable resin types. So we have some that we would choose for some projects. We have other that we would rather use for multiple shot or single shot molds. So it depends on the project and the material we're shooting with, depending on how we would design it. But for complex internal stuff, then we would normally use something that is dissolved. That's just easier for us and less. It's faster for us to design molds like that way.
And Stefan is asking, how many shots can you make with printed split mold? I guess there isn't a single answer, but guidance is appreciated.
Yeah. That's always the question we get. How many shots can we actually do from this? And our experience is that it really depends on the design of the part that we're using. If it's an easy to split, if it's something like a coin, easy, we can do more than a few hundreds. But the gear here, I think we actually did 100 parts in that one. But for us, it's not actually about the volume in it, because if we have a designer mold that works within the system, it's easy for us to print the same mold over again and then install it after X amount of shots. So for us, it's not the problem with the upscaling. It's more about if the part is, if we have enough draft, if we have enough parting lines and the way we need to ventilate the part when we inject it. So when the design is done, it's easy for us to print. So I'm mostly not afraid about the amount of shots and the amount of parts we can produce from a mold, because it's not really where the money is, rather than if the part is correct and if it's optimized to be produced in a printed mold.
So Jan is asking, how large items can you mold from a size and a weight point of view?
Yeah, I hoped to have another video, but let me see if I can show. So this is I'll just have to show here. So this is the Toyota part. It's about 13 times 13 centimeters. And this is just how big a block we ended up producing. But you can see when we're in the dissolvable mold, there's also a lot of resin that goes to waste for every shot we do. So that's worth to take into account. Then we have the lip here. Let's see, so I have the lip. It's bolted together of a few different parts, but I think that's like 15 to 20 times 30 centimeters almost as a block that we are combining. Again, that depends on how we want to make sure that we can take the part out. So it's about parting lines. We need to make sure that, so again, it's not really the big parts that are the problem. If we can print it in different parts that we can bolt together, then we also have solved that before. But of course, more than a size of a hand is always a bit more challenging than everything underneath that.
Right. So someone is asking, what is the 3D printer that gives you the best feedback to produce inserts? So from a surface quality and size tolerance point of view.
You say it again.
What's the best 3D printer for giving you these inserts? At least that's what I understand, Simon.
depend on the project again, because as you can see, when we start one project in one type of resin, we would normally rather stick to keeping that resin throughout the entire part, because then we know the fittings, we know the printer settings, we know the shrinkage would be more or less the same. So we are able to combine stuff, but we would rather just stay in one area. So about printing the surface qualities, it's more about the specific printer than it would be about the part. Does it make
Perhaps,
sense?
Tobias, you can also comment and let on that hybrid approach, because both when we talk about very large parts and when we want to talk about specific surface qualities that may be difficult to 3D print, that combination of metals and printed you were talking about makes a lot of sense to me. So perhaps you can share a little bit about that too.
About combining metal and
Yeah, exactly.
not sure I get the question totally. Maybe you can.
Well, what I found, at least based on my experience, is that when molds start getting very big, companies typically start looking for ways to recycle as much of a mold as possible. And that's where we typically see some companies start milling some parts of the mold and 3D printing other parts. The same approach can be used when you want to achieve a specific surface with, e.g., a high gloss finish, or
Okay, yeah.
that's
Okay,
what I
yeah.
was alluding to.
Makes sense. Yeah, we have done some projects where we're combining the metal inserts that would provide some of the surface quality of the parts. Also because we had some cores that had some really struggling for a head aid that needed to go inside the ear. So it's a super small features that they needed to get done, while the outside needed to have a specific surface quality. It's not that much we have. It's not something we have done much of, but we have tried it. But I think at this point we are more happy to try whatever rather than we have a extended experience in combining metal and print, unless we insert the entire print into a mold base.
So I was wondering, Tobias, perhaps you can describe a little bit about the typical workflow. Where do you start with the project? What is typically happening when a customer comes into your shop, so to speak?
Yeah, first off, we analyze the parts just for size. That's mostly the thing that we need to figure out, both the type of resin that we want to print in. So also if we have some crazy undercuts that are a lot easier to print in a dissolvable mode, then that's how we want to go forward. But then we want to quickly get in touch with the customer as fast as possible, because we can, with a few extra questions, we can probably decipher how we want to proceed with the task. So for us, it's good to have the first look at the part, but we can solve any part a lot of different ways, both cheaper and more expensive. So also to figure out where do we have some surfaces that are more critical? Do we have some cores that need to fit around and all of that? So I think normally we would just like to get in touch fast as possible.
And that also ties in with that 10-day development cycle. Stefan is asking if you do any rework before you start using the mold in the injection mold machine.
If we do any rework on the printed parts?
Yes, on the printed molds, yeah.
Normally not. We have tried to sand blow some of the parts, but I think we would rather just at this point where we normally have the customers in-house, if it's all about surface quality, I think we might want to solve it at a later point. Like this, we feel like people who arrive at our shop at this point in time is where they just need the first few parts in the correct material. So it's more material specific that they want to test out the material. Yeah. Then actually it's about the last finishing touch on the devices. So the small steps that you can see in a printed curve is where we would rather stay out of. At least there will be a lot of extra hours on our end to get that done.
Makes perfect sense. So I think my last question for today, Stefan has another one, which is, are parts in peak possible? That's
For
always
sure.
curious.
Always. Yeah. They for sure they are, and we have done multiple projects in Peak as well, so that's not a problem. But normally, when people want to request something in Peak, it's also a design that is not that easy. But let's see. Send me something, then we can have a look at it.
Good answer. So on that, perhaps any single advice for companies considering how to get started with 3D printed molds? What should people do? Well, the obvious one is, of course, reaching out to you, but what would you recommend?
I think it's a lot about figuring out where we are in the development stage, because this is I think we would really like to place ourselves right before production state. So when we have almost a finished design, but you would just like to test out the parts before you actually go into fully production molds, then you are able to get your parts in the correct material. You're able to do your strength test, your thermal test on the parts to get that reinsured, to capture some of the mistakes and the iterations that just cost a lot of money and a lot of time when you're in the final tooling. So that is where we see that we have a lot of where we can gain a lot with the customer as well, but they gain a lot of knowledge about their part before we actually they sign off a final production mold.
Excellent. So if nobody has any additional questions, I think I will conclude today's webinar by thanking everybody for joining. It's been a pleasure. I always enjoy speaking about this, but I also enjoy seeing things in action, and that's part of what you do a lot at Krebs Co. I'll be convening for the next webinar within the next week or two, and I look very much forward to reconnecting with you guys and everybody else. So have a nice afternoon, and we will be in touch soon. Bye.
Bye.
Thank you.
Bye.